So as you would recall, last time what we had done was just putting into in the form of permutation how all these moves can be written as permutations, right? So this was clear to us, the top one, and now we are going to see for other faces as well. So for the left one, what is happening is quite clear. 9 goes to 11, 11 goes to 16, 16 goes to 14, and then 14 comes back. So you have like this. And then what happens to the other one? 10, 13, 15, 12, 10. 10, 13, 15, 12 and back to 10. What about 1? 1 goes to in this move. So you are moving it. So this is the thing, and the left one is what you are moving, right? So you are moving it like this. Right? From here is a clockwise direction, right? And when you open the cube, you would realize that what happens to 1 in this move is 1 goes to 17, 17 goes to 41, and 41 goes to, well, the way cube is packed, this is opened cube, 41 actually goes to 40. So that you have to realize by experimenting. And similarly, what happens to 4? 4 goes to 20, 20 goes to 44, and 44 actually goes to 7. Again, the way cube is packed, and then 37 comes back to 4. And similarly, 6 goes to 22, 22 goes to 46, and 46 goes to 35. So we can write all this. F is like this: 17, 19, 24, 22, back to 17, and then 18, 21, 23, 20, and back to 18. And it also affects other sides. So for that, this is being written: 6 goes to 25. So this 6 goes to, when you are moving like this, it actually goes to 25, and 25 goes to 43, 43 goes to 16, and then it comes back to 6. So you have to identify all this. Similarly, for right you have this, for back you have this is back, and for bottom also you have this. Yeah. So this is what Rubik's cube is made of. Rubik's group is made of all these basic permutations, and I have written all these basic permutations. So if I do the left thing twice, if I move the left face twice, I will do the square of this permutation, right? So now what we can do is we can try to write it as a group. So I want group which is generated by these elements. So I want a gap, my software to remember a group, and that group is generated by, these are the basic moves, right? These are the moves. You remember 1, 3, 8, 6, 2, 5, 7, 4. These 1, 3, 8, 6, 2, 5, 7, 4, and so on. So I just cut and paste all this in the software, gap software. So I have put all this, and I enter. What it says is that I have created a permutation group with 6 generators, and you recall what are those 6 generators are? They are precisely T, L, F, R, B, A and B, all these things. Those are 6 generators of the Rubik's group. What is the first thing that you would do? Well, we may like to determine the size of this. How much do you think would it be? Millions, trillions? Let's see. Oh, I gave the wrong name. This is Rubik's GRP. And this much is the size. I can't even read. It's beyond billions, beyond trillions. So how to rectify this? I'll try to write it in the readable form. So factors of this, and I write it collected. I hope you remember last time I mentioned this command. So this is the number 2 to the power 27 times 3 to the power 14 times 5 to the power 3 times 7 to the power 2 and 11 multiplied with 11. It's a huge number, huge number. So I would show you an interesting anecdote. So this is what we have got, right? Size of Rubik's group is this much, 4325, and this huge number, the size of the Rubik's group. I'll mention an interesting quotation from this book called Innumeracy, Mathematical Illiteracy and Its Consequences. It's quite interesting book by John Allen Poulos, and it quotes, and this is the beginning days when Rubik's Cube was made. This toy company claimed that there were more than 3 billion possible states that Rubik's Cube could attain. They claimed in the beginning that there are around 3 billion different states. So this is one state, that is one state, that's one state, exactly one of the states is solid state. So they claim that it has more than 3 billion states. However, calculations show, so the calculation that we did just now using gap, it show that there are more than 4 into 10 to the power 19, right? So this is something like 4.325 into 10 to the power 19. The more than this possible states, 4 with 19 zeros after it. And then he gives beautiful analogy, says it's analogous to a sign at the entrance of Lincoln Tunnel stating New York population is more than 6. This analogy. Or McDonald's proudly announcing that they have sold more than 120 hamburgers. So this is the huge inaccuracy. This is orders of magnitudes of inaccuracy that was there in the beginning. Anyway, let's come back. Let's come back to our gap program by realizing that there are so many of the order of 10 to the 19 different states that Rubik's Cube could attain. So we have already factorized this, the huge number. So this is the size, and now is a crucial thing. So we have realized that there are 6 generators of it. So how do I actually solve? So first I construct a free group with 6 generators. So I just call those generators as T, L, F, R, E, just because I don't want to use B twice, so I am just using the notation E. So I am just having free group on these 6 generators. So let me just do that. So free group on 6 generators. What's the order of it? Well, free group is infinite. Just for fun, let's see. Order of F, infinity. So quite smart. Okay, so I have constructed a free group which is 6 generators, and now I construct a homomorphism from the free group to Rubik's group. Now that's a crucial part. So free group is something where operations, all the symbols are getting multiplied with themselves freely. So if I do it 4 times, I know I am going back to identity position, but in the free group, anything raised to the power 4 is not identity if the original thing is not identity. So there are no relations in the free group. So I want to use free group to understand this. So for that I will construct a homomorphism from free groups to Rubik's group. And how do I do this? Here is this command. So I group homomorphism by images. So I will specify that this element goes to that element, this element goes to that element, like that I would specify the homomorphism. So let us see what are the generators of group F and what are the generators of group Rubik's cube. So first, generators of, there is a command, I will paste that command here. So generators of group F are these, and then generators of the group Rubik's group are all these elements, right. So I will map T to this, T which is an element of free group, to this. Then I will map L to this, and then I will map F to this, like that, and then I will generate a homomorphism. Homomorphism is supposed to preserve relations, but then there are no relations here. So there is not much of the worry. So if T goes to this, the T square will be going to the square of this. So in that fashion I am going to have my homomorphism, and that homomorphism I can define in gap using this command, group homomorphism by images, and I am giving homomorphism from the free group F to Rubik's group, and generators of F, which are these T, L, F, R, E, B, they are going to generators of the Rubik's group, which are precisely the basic moves. So those basic moves are being mapped to. Okay, so let me define this. Copy it. So this is pasted. So homomorphism is created. So what is the homomorphism? This goes to this. So first T goes to that and L goes to that, like that. L is left and F is front and all that. So I have defined a homomorphism. Okay. So here is a free group. The homomorphism is defined to the Rubik's group. So I won't worry about relations because the free group is not having relations. And then let's just arbitrarily pick some element in the Rubik's group and look at its pre-image. So this element I have just written, but here let's pick some arbitrary element. So I am taking say X is a random element of Rubik's group, some element X, okay. And now what do I do? I consider pre-image of that element. So here I just consider pre-image of that element. Oh, this is some other element, but let me just take so in place of that I am just taking some element, say X, this is some element X, and the pre-image of that element in the Rubik's group. So let me explain what I have done so far. Here is Rubik's group, let me call it a huge one, let me call it R, and I have recognized generators of it, top, left, right, front, back, bottom. And then I have defined a homomorphism. Some 6 symbols. And for this there is no symbol. Back I didn't want to use B again. So like that I have defined a homomorphism. And as you would recall, as I am saying, suppose this is being denoted by hom, HOM, and hom of AB is same as hom A, hom B. So for that reason, automatically the T square will map to T square, like that. So I have defined this, and now what I do, I pick an element here. What is an element here? An element here is a state of the Rubik's cube, some random state of the Rubik's cube, that random element. So that's where I had picked a random element here. Remember this one, I have this random element, and then I am looking at the pre-image of this random element. So pre-image of a random element in this, suppose X is random element, is going to be huge. There is no one single element in F. So this is not 1 1, right? This is after all infinite group, this is finite group. So the huge subset of F which is there in the pre-image of X. So I am just picking one representative from it. So that representative will of course map to X. Anything that I take in that set is going to map to X. That's in the pre-image. So I take a representative in the pre-image, and that is a representative. This just is F into R into T into R inverse into F inverse into L inverse and E inverse and so on, like that. That's the representative in the pre-image. So I do that. And how much is the length of that? Well, let's see. Length is also a command. Length of whatever is the output from the previous command. Last, this case it's 98. In some earlier program that I had written, that I had done calculation for, it was 77. Okay, now I have already asked GAP to choose a random element. That's what we did the calculation, and we can actually look at the image of this. So whatever was X, we can look at the image of that X. Not T, is X. What's the image? So let me just see. So pre-image is this one, and what do we do with this pre-image? We just get all our moves. So we get that X is so our X has this random element X is certain combination. Say I am just for illustration I am taking say a pre-image of X to be say just for illustration T times L inverse R F inverse E B inverse R L something. So that is X, right? That is the state. So in order to get the identity element, what do? I just start with from here, other side, right? L inverse, R inverse, B E inverse F R inverse L T. So when I apply this move, then I will be solving my cube. So this tells you how I have obtained this state from the identity, right? How I have reached this state from identity. But that is reading in the free group. But if I do it in the reverse direction in the free group, what it does is actually solves the cube for me. So I hope things are clear to you. So if certain identity position is there, I am scrambling the cube, and unscrambling is precisely taking inverse in the free group, and that's what I am doing. So although this might not be the most efficient way, because the pre-image that I have picked is just one of the pre-images. I am not taking the pre-image which is shortest in length. So that's a drawback, but nevertheless, through all this we can understand that we can store first of all the Rubik's cube in gap, and then we can solve using gap using the idea of homomorphisms, and free groups are playing important role. And as you can see here, all these moves, the sequence of all these moves is nothing but a word, right? This expression, as you recall, is a word in the free group. So that's all. So everything is a word in a free group, all these moves that you are doing. So you should try to realize them as elements in a free group, right? So we can use these simple ideas by constructing Rubik's group, and then by considering homomorphisms, and then just taking the inverse image of any random element, and then taking the inverse of that word, and that's it. That is precisely how one can easily solve Rubik's cube, although I am not claiming that it is going to be an efficient way, because the pre-image which is going to come is not the shortest one, it is not of the shortest length. That is a small drawback. Similarly, what we did for whatever we did for 3x3 cube, we can also do it for 2x2 cube, and this time situation is much simpler. And the group which is there, earlier the group was S48, and this time everything is moving. There are 6 faces, so 4 into 6 minus 0. So S24 is going to be the group in which all the permutations are going to lie. It will be an interesting exercise for you to find out how much is the size of the Rubik's group for 2x2, and it will be wonderful if some of you are those who can easily download CAP software, then those people can solve Rubik's cube using this method. So now I hope you understand why we introduced free groups and homomorphisms. The purpose was to understand how gap stores all these things, and how we can use those things to solve Rubik's cube in this case. So it's a permutation puzzle. So all the permutations puzzle which concern scrambling and unscrambling something, they can be understood using these ideas. So I hope you could follow, I hope you could enjoy. If there is any difficulty, you can always contact us. Thank you.